All right, let's jump right into this explainer. Today, we're basically doing a masterclass on how to calculate and perfectly map out complex physical movements, step by step. As your physics instructor for this session, my goal is to hand you the exact mathematical and visual tools you need to confidently track displacement and really understand motion in a two-dimensional plane. Picture this. You're trying to navigate a motorboat straight across a rushing river. How do you do that without ending up miles downstream from where you actually wanted to go? Well, to solve a real-world navigational headache like this, we have to move way beyond basic numbers. We need to understand the true physics of displacement. Because you see, it isn't just about how fast your boat is going, it's about the very real forces of the water actively pushing against it.
So here's our roadmap for today. First, scalars versus vectors. Second, graphical vector addition. Third, analytical mathematics. Fourth, real-world applications. Fifth, uniform circular motion. And finally, some practice problems.
Okay, Section 1, Scalars versus Vectors. Let's build that foundation.
We need to clearly define the two kinds of quantities we use to track physical properties, because knowing your data type completely dictates how you can interact with it mathematically. So what exactly is a vector? Well, it's a physical quantity that requires both a magnitude, which just means an amount or size, and a specific direction. Plus, it has to obey specific rules of addition, like the triangle law. The absolute most crucial takeaway here is that a vector doesn't just tell you how much, it fundamentally tells you which way.
To really illustrate the difference, think about scalars. Scalars only care about magnitude. If you have a solid cube of aluminum with a mass of 2.7 kilograms, or say the temperature outside is 35.6 degrees Celsius, those are scalars. Standard everyday algebra applies perfectly. But vectors? Vectors are a whole different ballgame. If you're tracking a hiker's displacement away from a cliff edge, you absolutely need a vector because the straight line path and the direction matter entirely, especially to the hiker, right? Velocity, force, displacement, these are all classic vectors.
Moving right along to Section 2, Graphical Vector Addition. Let's learn how to draw these out.
Imagine we're at a 2D chalkboard right now. This is the head-to-tail method. Step 1, you just draw your first vector, A. Step 2, you place the tail of your second vector, B, exactly at the head, the pointy arrow part, of vector A. Step 3, you draw your final resultant vector, R, starting from the very first tail all the way to the very last head. Now listen closely because here is a super common mistake students make. They try to draw the vectors tail to tail right from the start. Actually, scratch that. Never do that for this method. Always make sure the head of the first directly touches the tail of the second.
But wait, what if they actually do start at the exact same point? Well, that's where the parallelogram method comes in, and it's a fantastic way to verify your work. You bring both vector tails to a common origin point, O. Then you simply sketch out parallel lines to complete a parallelogram shape. Draw a diagonal line right from that common origin to the opposite corner, and boom, that represents the exact same resultant vector R. Both graphical methods will get you to the exact same destination.
All right, Section 3, Analytical Mathematics. Time to get incredibly precise.
Graphical methods are awesome for visualizing things, sure, but real physics requires analytical math. This is where we transition from sketching to calculating. By resolving vectors into components along the horizontal and vertical axes, we can just add them up algebraically. For any vector A making an angle theta with the x-axis, its horizontal component is simply A cosine theta, and its vertical component is A sine theta. So to add vector A and vector B together, we just add their individual x components and then add their individual y components. It's like sorting a giant puzzle by color first.
Now, if you want to verify the absolute magnitude of that final resultant vector without relying on a perfectly drawn graph, we pull out the law of cosines. R squared equals A squared plus B squared plus 2AB cosine theta. Keep this one handy. It's an absolutely crucial formula for your toolkit, especially when you already know the magnitude of two vectors and the exact angle between them.
So, comparing the two side by side, we see exactly why physicists heavily prefer the analytical method. The graphical approach is highly visual and super intuitive, great for beginners. But honestly, it gets tedious, and it's limited by how steady your hand is with a ruler and protractor. The analytical method gives you extreme precision and makes it incredibly easy to combine multiple complex components, even if it does mean crunching more numbers.
Section 4, Real-World Applications. Let's take this math out of the classroom.
Let's go right back to that boat from the beginning of our explainer. We've got a motorboat with a velocity vector of 25 kilometers per hour heading due north. But the river current is giving us a second vector, 10 kilometers per hour at 60 degrees east of south.
By setting these tails at a common origin, sketching the parallelogram, and running it through that law of cosines we just talked about, we calculate a resultant velocity of exactly 22 kilometers per hour. We've literally just mapped its true, real-world displacement path.
And hey, this isn't just a trick for calculating velocity. We use this exact same concept to figure out the resultant force for objects being pushed from multiple directions all at once. Imagine you have a physical block. It's being pushed by 10 newtons of force to the north and simultaneously 15 newtons of force to the east. You'd use this identical vector addition process, resolving the components and calculating the hypotenuse, to figure out exactly where that block is going to end up.
Section 5. Uniform circular motion. What happens when straight lines turn into loops?
So, uniform circular motion happens when an object travels a circular path at a constant, uniform speed. But did you catch that? I specifically said speed, which is a scalar, not velocity, which is our vector. Even if the speed is totally constant, the actual direction of the object's velocity is continuously changing at every single microscopic point along that curve. And that brings us to a really fascinating physical paradox.
Because that direction is constantly shifting, the object is technically always accelerating, even if its speed never changes. Crazy, right? This continuous acceleration is directed straight toward the center of the circle. We call it centripetal acceleration, and the math is beautifully simple. Acceleration equals velocity squared divided by the radius of the circle.
Fun little history fact here, we actually owe our early understanding of this center-seeking phenomenon to the brilliant Dutch scientist Christian Huygens. He published a massive, thorough analysis of centripetal acceleration all the way back in 1673. He actually beat Sir Isaac Newton to the punch by quite a few years. It was a total game-changer for how we track forces in curved space.
Section 6. Practice problems. Time to put all of this into practice.
Grab your notebooks because here are 3 sample scenarios combining everything we just learned. Problem 1. 3 girls skate across a 200-meter circular rink to diametrically opposite sides using entirely different paths. What does that mean for their true vector displacement versus their scalar path length? Problem 2. A cyclist rides out to a park's edge, rides along the circumference, and goes right back to the dead center where they started. What's the net displacement? And problem 3. Calculate that resultant force we discussed earlier for a block pushed 10 newtons north and 15 newtons east. Try working these out on your own.
Which leaves us with a pretty fascinating, complex question to ponder. What happens when you introduce an outside pushing force to a perfectly uniform circular system? When you merge linear vector addition with centripetal acceleration, where exactly does the math say the object goes next? Think about how those different components would interact, and whatever you do, keep practicing your vector mapping.